Okay, all right. Well, Stats 102B, Summer Session C. Some of you were in my 101C class, and well, anyway, here we are. Stats 102B. We'll go over, I guess, well, welcome back to school. Welcome, summer session. Let's take a look at the syllabus real quickly, and it's posted here. So homework 0 is read through the syllabus and then sign these academic integrity agreements and stuff. But I think, and I hope I got this information correct. It's always so tricky writing out your syllabus and then realizing you made a mistake. So this is the hope that things are correct here. Okay, well, so we meet here, and this is it. We're gonna have a midterm week 3 and a final week 6 on Thursdays, and so that gives us a total of, we have a total of 12 sessions, and then if 2 are taken up for exams, then we have about 10 lecture sessions for content, and so that so each lecture kind of packs a punch, okay? And okay, well, anyway, this is let me see, is there anything that I need to do? So here's Campus Wire. I think that's set up. Okay, so it's TA sessions recorded. I don't know. All right, the Zoom link is there and will be posted. Okay, so all right, well, anyway, so my name is Miles Chen, and you can call me Miles or Professor Chen or Dr. Chen or whatever you're comfortable with, so that's fine. This is the office hour schedule. I'm gonna have to change this, because if everyone's meeting, everyone's gonna have discussion at 11, then I should probably change my office hours to something else like noon. So let me do a note to self to change that, and we'll go from there. Okay, here's our grade breakdown. Lecture review quizzes, Campus Wire participation, homework, midterm, and final. All right. Oh, okay. So those of you who are just arriving, I don't know, maybe I'll have to repeat this announcement. I told our TA, well, unless, again, if all the students decide to show up, I think it makes more sense to have the TA just have one discussion section at 11 a.m. Rather than kind of doing 2 things where we have a half classroom or something. Although, if everybody shows up, do we even have enough seats in this room? Let's see. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. Yeah, we do. We do have enough. There are enough seats to hold everybody. It'll be crowded, but there's enough room. Okay. Grading, I use a straight scale. All right, so the way the lecture view quizzes work is during lecture, this is what the view quiz would look like in the modules. So today is week 1, Tuesday. I would announce your view quiz answers. So, although I forgot what the answers are for this first quiz. So when you see the questions, they have no, there's nothing in here, right? There's no content, they don't test your knowledge or understanding of the class material or anything like that. It's really, I just give you the answer. And if you are here to hear the answer, then you will get the answer correct. And so, for example, today, week 1, Tuesday, let me look up what the answer is, because I I don't remember. Okay, the very first answer is the letter D. D as in dog. Okay, D as in dog. And I will give you the answers to question 2 and question 3 later on in today's lecture. And this is really just a test to see if you were here and listening and paying attention, or if you're not able to be physically present, the lecture is recorded and will be posted, and so you just have to kind of watch the lecture and listen for me to make the announcement of what the answer is, and that's that. Okay, all you have to do is you just click your 3 multiple choice answers. Please make sure you do not misclick. Okay, there's nothing really I can do. If you submit the wrong answer, you submit the wrong answer. This is intended to just get some free points just for coming to class. All right, it's intended for that. So question 1 today is the letter D. I will give you answers to questions 2 and 3 later, and that will be that. Okay. Make sure you do it before the next class. So today's lecture review quiz for Tuesday will close basically Thursday morning before Thursday's class starts, and then Thursdays will close Tuesday morning before that class. Oh, maybe I spoke too soon. Everyone's just showing up a little bit late. Okay. We have homework. And that's this is kind of your policy there, and then I'll have office hours. I got to kind of reschedule the office hours, I believe, but that is my preferred method for communication, is talking to you either in person or via office hours, and I use kind of email more as like a way to kind of keep track of records. So if we talk about something in person, I might just write an email follow-up that just says, as discussed, this is what you have, and that way you have kind of a paper trail for whatever it is we talked about, whatever accommodation we kind of agreed upon, or something like that. It's a little awkward to say, but I'm not good at email, in that if you send me a big an email with a lot of kind of stuff, and it's hard for me to kind of address everything, and so I think my preferred method of communication is talking in person or via office hours, and I'm available. I will try to make myself available at least multiple times during the week, and I'll reschedule kind of my Tuesday office hours, but I plan on having office hours Monday, Tuesday, Wednesday, and Saturday. And so hopefully one of those times will work out. And if not, you can still send me email messages, but please, be prepared for long, a long time before I reply or something. Okay. You can also send me direct messages on CampusWire. All right, so I think I've set up the link on CampusWire on Canvas, and I can also, maybe I'll send out email invites as well, and you can join CampusWire, and you can also send me direct messages there. Again, just written communication isn't my strongest suit, so it could take a bit of time there. Okay. I don't know. Are there any questions about kind of course policies, or just how the class is going to work before we start getting into some material and things like that? Okay. All right. Okay. So let's take a look. What is this class about? So this is 102B, and I argue that the whole kind of 102 series, fits in. If you think about what data science is, and it's kind of this this term and that encompasses things. And I'd say the 102 series, focuses on a lot of kind of these two aspects, the coding skills and the math stats knowledge, maybe with a little bit of a stronger emphasis on the coding side. And so there's kind of this diagram summarizing what data science is about. And there's kind of three broad areas: coding skills, math stats knowledge, and domain expertise. And it says data science is kind of the intersection of all three of these things, okay? And so I imagine most of you are either stats majors or data theory majors. Who is a different major? Not stats and not data theory. What is your major? Applied math. Okay, that's adjacent. Anybody else? Yeah. Math of computation. Okay, so it's also kind of the other adjacent side of this. But that pretty much encompasses the primary demographic. I mean, occasionally we will get like a philosophy major or something, but that's a broad, I imagine a lot of you are intending to pursue careers in data science or something adjacent to data science. So this is kind of what we have. And Drew Conway says, all right, we've got hacking skills, or I would say kind of coding ability. All right. And then you also kind of need to have your math and statistics knowledge. And so, if you're a stats major, you had to take kind of all of your prerequisite math, and then you have the whole 100 series, your probability and mathematical statistics and linear models. And if you're data theory, you get even more math. You get, these proof-based classes and analysis and things like that. And if you combine that with your coding ability, and that also encompasses math of computation and things like that, he says, that overlap is kind of machine learning, and there is a lot of machine learning aspects. And I would say that's what this class is a lot about. Coding ability, combining that with kind of math stats knowledge and doing some applications. Substantive expertise is the fact that because these statistics and data analysis stuff can be applied to so many different fields, it is important that you as a practitioner are familiar with that particular domain of knowledge. All right. So if you are going to be analyzing medical data, you should have at least a little bit of familiarity with some of these medical terms and images or something. If you're going to be working with, say, baseball data, you need to understand baseball. Okay, you don't want to be thrown into a situation where you have no knowledge or no experience or understanding of the data, just because being able to understand and recognize, hey, this is not normal, this is an outlier, this is something that shouldn't exist, that's going to be something that's clear to someone with domain knowledge and might not be something that someone else would recognize. So for example, if you're familiar with baseball, okay, and you see a player has, in your data set, somebody has a batting average of 0.55, all right? If you were familiar with baseball, you would say that is bizarrely high, okay? 0.55. Whereas in baseball, a high batting average would be anything over 0.3, okay? And a low batting average would be anything below 0.2. These batting average statistics, these values fall in this very narrow band between, say, 0.2 and 0.3, maybe 0.35 at the very max or something. And anything outside of that is very strange, at least for a season-long performance. Maybe in one game or two games you can get something really high like that. But if we're talking about the course of an entire season, of 162 games, having a batting average, say anything over like 0.55 would be bizarrely high, and you might want to investigate that and say, is this a typo? Did we mean to type in 0.25 rather than 0.55? Because the 2 is next to the 5 on the number pad and stuff like that. That's a possibility. And again, if you're not familiar with baseball, you would see that number 0.55. It wouldn't even register as anything unusual, right? Because you're just seeing a whole bunch of decimal numbers, 0.2, 0.3, 0.55. Who cares? All right. And you wouldn't recognize that. Okay. And similarly, if you are analyzing, say, kidney patient data, if you know nothing about kidneys and you see a number, right? Here's the measurement, and it's 17. You would have no idea. Is 17 normal? Is that really high? Is that really low? Okay. And so substantive expertise is very important. It's just we, as, say, the statistics department or math departments or whatever, we are not able to provide you the substantive expertise for every single possible field that you're going to apply this in, right? So if you want to go into finance, you better familiarize yourself with that kind of stuff, and you're going to have to do some studying outside of that. But this class, we're going to cover a lot of kind of these two things here. So that's what this says. 102B presents material from the overlap of coding skills and math and stats. The Venn diagram says that this is machine learning. Indeed, we will cover some machine learning algorithms. 102A is a prerequisite for this course. And so I am assuming everybody did fine in 102A and is comfortable with writing code there. And what this course is hoping to do is it is hoping to prepare you for data science work by kind of looking under the hood on some of these kind of machine learning algorithms. And we're going to be spending a lot of time in this course, at least in your homework. All right, at least in your homework, you'll be taking a lot of kind of these codes, and you'll be kind of writing them yourself. Okay, you're going to be creating, like, it's as if you were taking some kind of engineering class, and you have these take-home projects of like building, a small bridge or something like that. Okay, you're going to be creating kind of like little versions that run on your computer and things like that. Now, granted, pretty much all of these algorithms and stuff that we are going to cover have already been coded up, have already been implemented in these very good performing, very reliable packages and bits of software. Okay, so you can just call in, library this and library that. Okay, and that's the package you should use in real life, right? Like when you leave this class and you get a job doing data science and data analysis, don't write your own KNN algorithm. Don't write your own, k-means clustering algorithm or something like that. Use the package, right? Those are designed professionally, right? It'd be like, you wouldn't take your own, I don't know, I guess in some class, maybe you make your own little windmill or something, and you wouldn't use that for like power generation, all right? You would buy some kind of professional industrial strength thing there, and similarly you would use these packages. But the hope is that by kind of giving you the task of writing your own code and implementing these algorithms yourself, you gain a deeper understanding of the tools that you're using. Okay. So this is a lot of kind of stuff that we're going to cover. We're going to cover kind of key concepts from machine learning: loss functions, likelihood functions, cross-validations, regularization, and then we'll look at some of these different models or algorithms: linear regression, neural nets, MLE, classification, et cetera, et cetera. Okay. I will admit, there's different people who teach 102B, and there is a description of the course in the course catalog. And this course does fit that, but I also take a lot of kind of liberty and bring in a lot of other stuff that I want to cover. Like, for example, neural networks is not part of the course description, but I think it's an interesting topic, and we get into it. Okay. This class has a lot of overlap with, say, Stats 101C, which I taught earlier this summer. And so in 101C, we covered a bunch of different kind of machine learning models, things like random forest, linear discriminant analysis, and SVM. Actually, we will touch on SVM today, and generalized additive models and things like that, and their applications. And this course covers a lot of those kind of algorithms, and in this class we're going to write our own code to implement them. Whereas 101C, the focus was more on the application and was more focused on, here's this high-performing package out there. And with 101C this past summer, I used tidy models as a way to kind of the framework that we implemented it and stuff. And we just said, hey, here's the data, you apply this thing, can you make good predictions and something like that. So we're going to be covering a lot of the similar kind of names and topics of these models. This one's going to focus in on, like, how do you build this yourself? How does it work on the inside? Whereas 101C is like, how do you apply it? And what kind of stuff does it output there? Okay. All right. And as far as if you are majoring in stats or data theory, or these are all of these classes, and I imagine a lot of you have taken a lot of these courses already. Just kind of the foundations are laid out in the lower division kind of courses. Your Stats 10 provides some just foundations of statistical thinking, and then in Stats 20 we introduce you to R. The 100 series is all about the math. All right, going back to this Venn diagram is all about kind of the math and stats knowledge side there. All right, 101A and 101B, I would say those cover statistical models where data is expensive and interpretability is important. So in 101B especially, you do design of experiments, and there's kind of, when we talk about data science and data in general, there's kind of two different approaches, and one is a place where data is expensive. All right, so you think about a medical study, okay? A medical study, and you want to do, experiments with volunteers, people, maybe patients who have some kind of disease, and you want to know if this particular experimental medical treatment is effective. All right? Well, every patient that participates in your study might cost you tens of thousands of dollars to gather data upon, right? Because gathering that data requires paying the doctors who are going to be working with the patient, paying, the nurse and the support staff, right? And you have to maybe, the experimental medication or whatever, that's expensive just to develop and stuff. And so you figure every single patient who participates in your study represents thousands of dollars of investment, okay? And so with a budget of, say, $100,000, you might be able to get data from 40 patients or something like that, okay? Or, you might spend even more money or something. But again, your entire table of data might have 40 rows, okay? And you feel like, oh, that's a really small data set or something. This represents, thousands and thousands of dollars of investment just to gather this data. So how do you design your experiment so that the data you have can be most effectively used? That's what 101A and 101B, I think really, especially 101B, the design of experiments is so that when you are working with the data, you're not unnecessarily collecting huge swaths of data that you don't need. Did you guys, I think I asked my 101C class, but did you guys take 101B already? And did you have a project? Yes, no? Okay, and then where did you get your data for that project? I'm just curious. What was the project? Nobody?
We were given a cardiovascular data set and we had to run, I think we used a random forest and we had to just see which, or one of these, we had to design a matrix and see which variables affect the cross-validation.
Okay. Huh. All right. So you didn't know data collection yourself?
No.
It was just like in a ANOVA application with a Latin square or something.
Yeah.
Okay. All right. If you had to collect your own data in some kind of simulated something, you'd realize in certain situations it's annoying and to collect data. And you might have started off with great ambitions. We're going to get data from 250 people, and you realize I don't have the time or patience to have to collect data from 250 people. Can I get away with doing only 100 people? Can I get away with only working with 50 people? And in a lot of cases, you do a power study and you say, okay, well, how much of a difference am I expecting? How many samples of data and observations do we need? And you can do something like that. All right. Whereas on the other hand, 101C, 102B, these are kind of models that we deal with when data is cheap, okay? And that you're going to get download data from a web server, which has been logging everybody's clicks, right? And so now you have millions of rows generated every single week, okay? You got these huge amounts of data, and we're just trying to detect little patterns in there. We're trying to make good predictions based off of this thing, right? You're thinking about internet ads. How many of those links get clicked? All right. So, one thing I wonder, right? So you go on Google, or I guess this is searching for Bing, but let's say I decide I want to go to Priceline, okay? And so you type in Priceline, and the top two hits are ads. This one is Expedia, this one is Priceline, and this one's Cheapo Air, this one's Flight Gorilla. Okay, and then Priceline is the number one actual result that's not an ad, okay? So I guess the question is, so Priceline is actually the number two. So when I type this in, okay, do I click that? I might click this, the ad, or I could scroll down to the first thing that's not an ad, right? And they'll both take me to the same place. And then, so the question is, how much should Priceline have to pay? If you're this company and you're like, why do I have to pay for ads on my own name, and versus let's see, what happens if I type in UCLA? Okay, so obviously UCLA, we're not running ads on ourselves, right? But we type this in and we get this, right? So I'm thinking, I don't know, is the result different from Google? So, okay, yeah. So same thing. Priceline has to pay money to get their own link on their own search term. And it's right, if you click this, now Priceline has to pay Google money, or you could have just scrolled down a quarter inch and you could save them, I don't know, whatever this is, right? And apparently this is happening because Expedia is just we're going to pay money so that we show up as the number one ad result or something, right? Well, anyway, all of this data is being tracked, and obviously Google wants to make as much money as it can by selling these ads. And obviously, Priceline also doesn't want potential customers to go off to Expedia because Expedia is outbidding them on the ad, right? And so all of this stuff, they're gathering this data. If you have a Google AdSense account, they send you all of this data, and you want to know, okay, well, do I have to up my bids on all of these ads and things like that, or is this fine? Okay, and it's hard to know, but that's kind of what we're trying to do. Okay, I got to talk a little bit about academic integrity. So, I try to write homework assignments that will be interesting and challenging and also rewarding. And that's kind of a tough combination, all right? Sometimes it's too challenging. Sometimes it's not challenging and not rewarding. I don't know, right? And then sometimes it's not interesting, right? It's and some of these homework problems that I give you, they're going to be tough. And I'm going to ask you to write some code. And the truth is again, all of these algorithms and stuff have already been implemented. And the point is for you guys to build it yourself. And there's learning that happens when you have to build these things yourself, right? Like when I don't know, I imagine somewhere in middle school or high school, you built your own, I don't know, something, solar car or something, right? And there's something educational in that thing. And the truth is if you go on the internet and you search for solutions, you can go on GitHub, you can go on Stack Exchange, and you can say, well, how do you write code for doing something like this? And you'll find your answers, okay? And that would be great if the goal is to get the job done, okay? Once you graduate and you start working, and your boss says, hey, we need you to do this thing, don't feel bad about using the internet to look up help and say, well, how did somebody else do this thing? That's a reasonable thing to do, okay? For this class, however, the goal is not that you accomplish some kind of task, okay? I don't care that you were able to sort the points using KNN, okay? That's not the goal for me. The reason why I assign the homework is for you to have this learning opportunity of kind of coding this up yourself, okay? And kind of the analogy I like to use is if you think about going to the gym and working out, and you think about like, why do we lift weights at the gym or something, okay? The goal of lifting weights is not so that weights get lifted, okay? The goal of lifting weights is that the process of the person lifting the weights will gain strength, okay? And if the weight training, no pain, no gain, I think that's a concept we understand, is that, if your weight training or whatever your exercise you're doing doesn't result in a little bit of soreness or pain or, exertion, okay, you probably didn't exert enough to expect muscle gain, all right? And experiencing muscle soreness in that case is a sign that your muscles will go through repairs and get stronger, okay? Similarly, your brain is similar in that if you only do jobs and tasks and puzzles that are easy for you, then your brain will see no reason to have to work hard and make additional neuron connections, when you go to sleep and stuff like that. Okay. On the other hand, if you present yourself with challenges and puzzles and tasks that are tough, and your brain has to think, and you get tired from thinking about all of these things, then when you go to sleep, and rest is important, your brain's going to say, hey, can we form some new connections, neuron connections here that are going to make better pathways that are going to make us better at this thing, and you become better, right? It's just it's like, I don't know if you drive, but the very first time you sat behind the wheel and you drove, it was overwhelming. There was a whole bunch of stuff, all these knobs and pedals and things and levers, and you have to kind of take in all of this visual and audio stimuli. And in the beginning, you drive very slowly and you're cautious, and I don't know, a few years later, driving becomes something that's a little bit more second nature, right? I mean, if you think about a baby learning to walk, its first steps, it's very shaky and unsteady. And then, of course, now everybody walks. I mean, not everybody, but, walking is something that's we don't have to think about, okay? Similarly, coding, especially if you're newer to this stuff, it's going to be tough. And then after a while, you get better, right? I didn't really write code until I entered graduate school, okay? I hardly did any coding in my undergraduate studies, and I didn't start writing code until I was in grad school, but I worked at it a lot, right? And now my job is mostly teaching some of these coding things. So there's a lot that you can learn, okay? If you plagiarize code for a difficult assignment because you're having trouble, that's like going to the gym and then asking somebody else to lift the weights for you, right? And if you do that, then great, the weights got lifted, but are you going to gain any benefit from it? Okay, you're not. You're not going to gain any benefit by having somebody else lift the weights for you. And similarly, if you copy and paste someone else's code, sure, you might get your homework done, you might get your points, but again, the whole point of the homework wasn't for you to get your points. I mean, I understand that's a goal that you want, but that's not the point. That's not why I'm assigning the homework, okay? The goal is to present kind of this challenge that stretches you to become better at coding, okay? So if, I think students who resort to plagiarism or something like that, I don't think it's because students are lazy and evil or something. It's just, I think these students who choose to plagiarize, they've confused the goal of the course. They've got mixed up in thinking that the goal is earning the points for the homework and not the learning aspect, okay? And that's the wrong way to approach this. The goal of the course is your learning. Now, I admit a major conflicting issue is that I'm not able to kind of create individualized grading schemas that evaluate exactly how much you've learned, and so I have to kind of evaluate you on whether your code works and stuff like that. And everybody's kind of graded on the same criteria. But I hope you yourself personally can judge your performance in the class based on what you learned and not just your letter grade or things like that, okay? So anyway, when you face these challenging homework assignments, I want you to work hard. I don't want you to look up answers or view someone else's answers, okay? Either that's, a classmate, current classmate, or former student or something. And if you're not able to complete the homework to 100%, submit what you have, all right? And, if you don't complete it, you're not going to get 100% on the homework. But I hope you're okay with that, right? And you see this as a reflection of your current coding abilities. This is someplace where you can grow and improve. And that's the hope, right? I don't want to have to report anybody for plagiarism. I don't want to have to deal with the student conduct office. If we have to, we have to, and we will. I have done it where we've escalated cases to the dean and things like that, but I don't want to. It's not a fun process for me. It's not a fun process for any of the students involved. So, so please don't just be honest in all of this, right? There's a collaboration policy that's online for Homework Zero, and please read through it and sign it. And when you discuss things on CampusWire, you can discuss how you approach a problem, some ideas there, and you can do it without necessarily sharing actual lines of your code. All right, so that's kind of the one thing that I don't want you to do is share lines of your actual code. Now, if we're talking about that doesn't mean you can't have any code written anywhere on CampusWire, right? So there is a lot of coding. It's a coding class. Coding. If you have any kind of questions about the code that you see in lecture, questions about code, or for any of these topics, feel free to post those code questions and ask stuff on CampusWire. It's just I don't want you to write like, hey, is this code what you wrote for homework problem 2? Okay, that's the thing that's off limits. Okay, you can say, hey, what approach did you use for homework 2? And you can respond and say, oh, you know what, for homework or problem 2, I created a vector that did this and I applied this function to it, right? And there's a lot of ways you can kind of explain an approach without necessarily writing the exact lines of code there, okay? I want to take a little aside and just talk a little bit about grades and life. And this is, you know, I want to say a little bit here. Okay, so number one, your grades do not define you, all right? So you guys are here at UCLA, and I imagine that the reason, a major reason why you got into UCLA is because you were a very good student in high school, okay, or at community college, right? You poured a lot of energy into your classes, into your grades. You were a high-performing student, and that's why you were admitted to UCLA. And because of that, you're kind of coming from this history where grades were very important in the past, and grades still feel very important to you, right? But that said, again, your grades do not define you. You know, it feels good to get good grades. I understand that. You know, grades do play a role in, say, grad school admissions if you're thinking of going to grad school. But again, it's not the most important thing in life. And, you know, if you imagine yourself, you know, 60 years into the future when you are an old person, you're not going to look back and just say, oh, I can't believe I got a B plus in that class. I should have gotten an A minus or something. You know, I wish I did whatever it took to get an A minus or something, right? Those are not going to be the things that you remember and recall. I mean, and so I have story time written here. And, you know, just a little story from myself is that in high school, you know, I worked hard and I got good grades in high school. And I was never the popular kid. I didn't do much athletics or things like that. I studied and I did well in classes, and I felt good about that, and I felt okay with everything else because I thought, you know, I've got my grades and I'm happy. I'm going to go to my college and that I want to go to and stuff. And you know, my senior year, I got into my dream school, which was Caltech, California Institute of Technology, and I was very proud that I got in and I enrolled. And so that fall, I started at Caltech. Caltech's also on the quarter system, and so, you know, that first fall quarter, you know, those 10 weeks of classes, they kicked my butt. And in fall quarter, I got my first C ever, you know, the first grade letter of C, and I was like, oh my gosh, okay. And then winter quarter, I got my first D ever, and then spring quarter, my freshman year, like everything kind of fell apart and I failed multiple classes, okay? And, you know, and that process, you know, it wasn't like a shock that I was failing all of my classes, right? By the time like week 5 or week 6 was coming around, I knew I was like struggling. I wasn't going to make it. And that just kind of created this kind of spiral of just like self-loathing and like feeling overwhelmed and not able to get started on things. You know, I was depressed whenever I thought about my classes and my academic situation. And so anyway, I failed a bunch of classes my spring quarter, my freshman year, and I was put on academic probation, and I was warned that if I don't get my grades up to a certain level, I'm going to get kicked out of school. And so that summer, the idea of like returning in the fall to more classes and having to retake all of these things, that was overwhelming and depressing. And you know, the problem was I had tied so much of my identity to my grades. You know, to me, when I performed well in classes and I got good grades, it was like, I'm doing well as a human. I'm doing well as a person. This is where all of my time and energy is going, and but it's paying off because I'm getting good grades. And so when I failed those classes and I got bad grades, and I had tied so much of my identity to those grades, and the grades were coming back as Fs, I felt like a failure as a person. I'm very grateful to my parents, especially my father at the time. He was very supportive, and he said, I know it was your dream to go to Caltech, but if this is what's happening, it's not worth it. And basically, it brought me to a point where I felt okay letting go of this dream of attending Caltech. And so that summer, instead of returning back to school, I ended up transferring to another school. I ended up going to a small engineering school in Michigan. I think the change in scenery was nice. Also, the classes were not as intense, and I was able to kind of also distance myself from that. I was divorce my identity from my grades. Okay, and that change, I think just dramatically just improved my approach and outlook and things like that. And so, I share that with you. It was a painful time going through that, experiencing that failure, and again, but I'm grateful for it because it allowed me to separate how I view myself. Okay, today I don't view myself as, if I'm doing well academically or now professionally, that doesn't change my view of self. Okay, and if something is happening, is not going so well academically or professionally or something, that also doesn't change how I view myself. I was able to find my self-worth not in my grades, my own personal faith and my relationship with other people is, now where I find value and things too like that. But yeah, so anyway, I don't know where you are and where you stand in terms of your relationship to grades and academic or professional success. But I want to kind of allow you to separate yourself from that. And so don't tie your view of yourself to your grades and things like that. Okay, and I get it because I was that person, and I I felt good when I got good grades, and it still feels good to get that reward. But that's not why we're living, right? You are so much more than just your academic achievements, and when you move on from here, you are also so much more than just whatever professional achievements you have or whatever professional title or whatever salary number it is. Okay, that you're much more than that. So I hope none of you ever have to go through a demotion or something, but even if something happens, or you're laid off or fired from your job or something, that doesn't speak to who you are as a person. Okay, you're so much more than that. I want to talk a little bit about kind of a work-life balance, and I know this is totally off topic and everything, but at the same time, sometimes I think this is perhaps more important than any of the academic stuff I can present. Okay, and I think this is something that I know a lot of students struggle with, and I know a lot of people struggle with professionally, regarding how do you find a balance between your work obligations or your school obligations and the rest of life, right? And so I put three broad categories for where your time goes. One is work, okay, and that's going to be your literal jobs or internships. The others will be, that also includes academics or any other kind of professional obligations. If you're the leader of some kind of club or something like that, that I would put that under work. Okay. Another broad area of your time is relationships with other people. Okay, that's going to include family, friends, if you're in a romantic relationship, or any other kind of social obligation that you have that falls there. Okay, and then lastly, you have care of self, right? And that includes care of your physical health, your mental health, your spiritual health. And the truth is there are 24 hours in a day, and it's not possible to give 100% to all of the categories that everybody is asking from you. Okay, you cannot give 100% to every single one of these categories. So how do we achieve work-life balance? And I say work-life balance is achieved by consciously choosing what is important to you and devoting your time and energies accordingly. Okay? In general, the more you put in, the more you get out. Right? You have, now there's an exception, you have kind of toxic relationships, toxic workplace environments where you put more in and you get nothing extra out of that. Okay? In general, the way it should work is the more you put in, kind of the more you get out. Okay? Sometimes that's not always the case, and it's important to be able to identify those things. Okay? And I think you can find satisfaction by accepting what happens, the natural consequence of when you choose to put less time into something, you're going to get less out of that. And if you can accept that, then that's just a natural consequence of what's going to happen. I think you can be satisfied. So here's kind of a silly example. Let's say you are a part of a group of friends, okay? And one day you start dating someone, you get involved with a romantic partner. And so now that you have this new person in your life, you're investing a lot of your kind of relationship time, okay, into your romantic partner, and you are developing, a stronger relationship with this romantic partner, okay? But now you're spending a lot less time with your original group of friends, and just naturally what happens is when you spend less time with your kind of original group of friends, you might just grow a little bit more distant with them, okay? And when you see that distance forming, it might initially feel hostile, but this is probably not the result of your friends being angry that you have some kind of romantic partner, but just the natural consequence of what happens when you spend less time with people, right? When you, perhaps your initial group of friends, like they go out to see a movie without you or something, and you feel like, oh man, why didn't you invite me? And they go, well, you've been spending, all of your time with so-and-so, and, we're not angry with you or anything. It's just, we didn't think you were free or something, right? And you just be like, oh, I wish you would have at least given me the chance or something, right? It's just naturally what happens is when you spend less time with people, you're going to be as close before, right? And so you as a person, you and we as people we have to choose, and we get to choose. We get to make a choice about what is important to us. And when you can kind of accept the natural consequences of what happens when you invest less time into something, you can, reduce your own feelings of bitterness and jealousy, okay? Perhaps in the corporate and professional world, people who devote a lot of time and energy into the goals of the company, a lot of times those people are rewarded, right? The company isn't necessarily punishing people who choose to have families and a life outside of work, okay? But, from the company's perspective, who should they promote, right? There's the person who did everything that was asked of them, and then they continued to stay at work and did even more, okay? Or there's the person who did everything that was asked of them, but then as soon as they finished what they were doing, they left, and they went home to their family or their friends or their romantic partner or something like that, okay? Now, this person who stays at work and does even more, it might be because they don't have much of a life outside of work, so they continue to invest all of their time at work. But, from the company's perspective, it kind of makes more sense to reward this person than this person, right? And, you get to choose what's important to you, right? If climbing the ranks within the company is more important, then spend your time accordingly, all right? If spending your time with your family and friends or romantic partner or whatever is more important, then spend your time accordingly, okay? It's just, it's difficult to be able to give 100, it's just not possible to give 100% to everything. So, spend your time accordingly. I also say self-care is important. Don't forget. So again, with the kind of our three broad categories, we got work, relationships, and self. And don't ignore the self, okay? So don't neglect taking care of your physical and your mental health. If you neglect care of self, you're less likely to be operating at 100% efficiency, and the time you spend on other things, whether your work, school, relationships, won't be as productive. So for example, if you don't get enough sleep and a friend invites you out, maybe you choose to accept your friend's invitation instead of sleeping, but you're a little bit of a drag to be around just because you're tired and lacking energy, okay? Or say exams are coming up, right? Maybe you choose to skip meals or minimize sleep in order to study, but you end up getting sick or something, and your performance on the exam suffers because of it. And perhaps maybe it would have been better to just eat properly and sleep well, and maybe study a bit less. Okay, so those are things, right? And when we say things like your physical and your mental health is important, that's not just an empty platitude that we're just saying so you feel good or something. Okay, that means I'm encouraging you to invest your time into activities like exercise, sleep, and relaxation that will boost your physical and mental health. And sometimes that means you're not going to complete your homework to 100%, okay? And if you don't finish your homework, the natural consequence of that is you're not going to get 100% on your homework grade, all right? But I want you to be okay with that. I want you to be able to say, you know what? In this day or this moment, it was more important for me to rest. It was more important for me to take care of myself. I didn't finish the homework, but I'm okay with that. I'm okay with getting the lower grade on this thing, and that's okay. And I want you guys to be okay with that, right? I also wrote this. I said, entertainment and fun activities are important for your well-being, and it's true. It's important. It's very important to have fun. I'm a big fan of entertainment. All right, I love watching TV and movies and sports, playing board games, video games, whatever. Right? All of those things are good. Okay, and participating in an entertainment activity, what it should be is it should be a break from work. It should give you a mental energy and mental health boost so you can kind of return to your work in a better mood, all right? But the truth is some activities, and even possibly hanging out with certain people, can have the opposite effect. That after you participate in this activity, you find yourself drained, right? And there are video games, there are apps, social media sites that are designed to be addictive, okay? And they give your brain little immediate dopamine pleasure hits. So you keep playing them round after round, or you continue scrolling or swiping forever and keep coming back to these apps. But the thing is you can spend hours of doing this activity, and at the end of it, you don't feel any good, right? You feel like, oh man, how did it end up 3 a.m.? And what did I accomplish? And you just kind of feel bad about yourself, right? Or maybe you're like, oh, I'm gonna spend this day doing this thing, and then you spend all day playing round after round of some video game, and then and then you just kind of feel a little bit like trash at the end of the day. That's not a good thing, okay? That's not a good sign. That's probably a sign that this is a fruitless bit of entertainment. And so, just be mindful and selective about your entertainment activities. You should be having fun, but yeah, that's the point, right? Don't just get sucked into some of these addictive things that pull you out, where you hide from your responsibilities or something. Okay. Okay, let's get into some actual content here, and let me give you your second view quiz answer. Second view quiz answer is the letter A. A as in apple. So week 1, Tuesday, second view quiz answer is A. A as in apple. All right. So let's just introduce some machine learning ideas, okay? So this is what machine learning Wikipedia says is machine learning is all about. It says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without using explicit instructions, relying on patterns and inference instead. I take this and I say, you know, the big idea here is we're going to fit models to data. You know, you as people still have to make a lot of decisions regarding kind of how that model is specified, but a lot of decisions are guided by the data and the algorithms that are used. And the fact that the decisions are being made by the algorithm, that is the part where we say the machine is learning, okay? What's a model? Here is a picture of a model airplane, okay? What is a model? So this model airplane is a simplified representation of a more complicated thing, right? So the more complicated thing is the real airplane, millions of dollars, possibly billions of dollars, depending on what we're looking at, okay? So the real thing is a very complicated system, and this is a simplified representation of it. That's what a model is, okay? And so when we talk about a statistical model is a simplified representation of a complex real-world process that generates data. So in the real world, there's some kind of process that generates data, generates the values that we see. And a statistical model is a simplified representation. It's not the actual thing, it's just a simplified version of it, okay? So if you think about, all right, what are all of the factors that go into determining someone's height? Okay, lots of things, right? You have your parents' genetics, you have environmental factors, and the environmental factors that include things like, you know, your nutrition and how many calories and how much calcium and how much sunlight and all of these different things, and it's complicated, right? Maybe even like what kind of bed you sleep on. I don't know what affects people's height, okay? And a statistical model is going to just be a simplified version of the different relationships that between variables that exist in the real world, usually only looking at a subset of variables and that are related to the outcome. And they're always going to have to include an error term to account for everything else that was not part of the statistical model. Okay, so when we talk about models, there's kind of two general approaches. All right, two broad approaches. One is we can use the models to make predictions, or we can use models to gain understanding of the relationship between variables. And we often have to make a choice about which of these goals are more important. Is it more important to have accurate predictions, or is it more important to have an understanding of the relationship between variables? Quote is, all models are wrong, but some are useful. Kind of the idea that, yeah, again, with the model, it's always a simplified representation. It's never going to accurately represent what is actually happening, but they can still be useful for us to understand. So, okay, you need the textbook, and I forgot. This is the book. Okay, that's kind of, all right. Well, all right. This is the textbook that we use, and so I'm going to be using an example from this, and I've assigned a few homework problems from the textbook, so you'll need to get the textbook somehow, okay? All right, so we're going to look at some data from the Olympics. So this is the 100-meter dash, the foot race with like Usain Bolt and people running, okay? And we're going to be looking at the gold medal time. So how fast was the runner that won the 100-meter track and field event, okay? And if you think about, okay, what factors into the winning time? In the real world, there's a whole lot of things that there's the athlete themselves, I don't know, all sorts of things, okay? But we're going to look at this relationship at how fast the time was just over across the years, okay? And this is what our data looks like. So I think the first bit of data that we have is from the 1896 Olympics. And the winning time was 12 seconds. And then we had the 1900 Olympics, and the winning time was 11 seconds. And then we had 1904 and 1908 and so on and so forth. And we had different Olympics. And what we see is that kind of as time has gone on, the winning race time seems to have gotten faster and faster, okay? In the year 2000, it was 10 seconds, maybe a little under 10 seconds, I don't know. 2004, 2008, 2012. And we've had a few more Olympics since then, okay? And so how do we summarize this relationship? Well, we might say overall, the trend is as the years have gone by, it seems like people are getting faster. At least the winning race time has gone faster. At least that's what has happened over the past 100 years or so, okay? And so if we know the year of the Olympic Games, perhaps we could predict the winning race time. We can say, well, in the year, can you guess what the winning race time was in 1960? Can you guess what the winning race time was in 1950? Or whatever one was divisible by 4, okay? Something like that. And so we might create a linear model, a straight line model. And for it to be linear, it means the amount that we adjust our prediction remains a constant through time. So if we say the time has improved by 0.05 seconds, going from 1920 to 1924, so in that 4-year span, if we're saying the time drops 0.05 seconds, then our prediction going from 2000 to 2004 will also be 0.05 seconds, okay? And every time we bump up another 4 years, we're going to, our time is going to improve by 0.05 seconds, okay? Now, we would not want to try to predict values in the distant future, okay? So by the year, whatever, 3000 or something, we're going to be in the negative territories or some negative numbers, but this model could still kind of be useful, okay? So, I guess 200 years into the future, we'd be at, 1 second race times, and that's obviously not going to be the case. Non-linear means that the amount that goes up is not going to be constant, okay? So linear just means the amount it increases is a constant value. So we have, fitting this model, okay? And so you're already familiar with linear models, but as far as this thing, a simple linear regression model, we're trying to estimate slope and intercept, okay? And fitting a model is the idea, or is how do we estimate the model parameters? How do we figure out the best value for the slope? How do we figure out the best value for the intercept? And the idea is we want the resulting model to do the best job of fitting the data. Best job of fitting the data. So how do we define what is the best, okay? So when we say we want to fit a model so we have the best parameters, how do we define the word best, okay? And how you define the word best is carried out through your choice of an objective function. And so when we talk about ordinary least squares regression, the best is the model that minimizes the squares, right? Minimizes the total squares of the residual being the actual value versus minus the predicted value. The difference between the actual value and the predicted value, that is our residual. And least squares regression says the best line is the one that has the least amount of the squared residuals, right? There's other forms of regression. There is like minimum absolute deviation. So instead of taking the squares of the residuals, you take the absolute values of the residuals, and you're trying to find the line that minimizes the absolute values of those residuals, all right? That's the minimum absolute deviation type of regression, and that's something else, okay? But here for ordinary least squares regression, we're going to say we're going to minimize the squares of the residuals, okay? And so this is what we call the objective function. That is the objective, right? What is your goal? This is the objective function. And because we're trying to minimize it, sometimes this is called a loss function or a cost function, because in general, people want to minimize their losses or they want to minimize their costs. And so we might call this a loss function or a cost function. All right. I think so far so good, okay? And so a lot of machine learning models, and linear regression counts as a machine learning model, try to fit parameters by trying to minimize or maximize an objective function. And a lot of machine learning problems can be kind of just reframed as optimization problems, right? And so this course is called computation and optimization and stuff. And so I know linear regression is review for you, and you've seen this many times already, probably. But we're going to kind of look at it again, so to kind of introduce and familiarize you with a lot of concepts in machine learning. Now, in the textbook, I'm going to try to match the notation of the textbook. Okay, the actual values in the textbook are not y, but they use t sub n as in target value. Okay, this is the target value. This is the actual value that we're trying to predict. All right, and the values predicted by the model. Okay, all right, the model has parameters W0 and W1, the intercept and the slope. Okay, intercept and slope are W0 and W1, or weights 0 and weight 1. And we're going to say the value predicted by the function for observation x of n is going to be f of xn given the parameters W0 and W1. Okay, that's what this is. And so yn minus y hat will become replaced with t sub n minus f of x of n given parameters W0, W1, right? And then we're going to square these things. Also, the text likes to use the mean squared error rather than the total squares. And so all we do is we just take the total squares and we divide by n. So we multiply that by 1 over n. And the solution that minimizes mean squared error is going to be the same solution that minimizes residual sum of squares. So the loss function is going to be looking like this. All right, is that okay for the notation there? All right. Okay, and then a common function that we also see is the root mean squared error. This is a very common function that people try to optimize or minimize, and so this is a lot of ways how we evaluate things. Root mean squared error is basically the square root of the mean squared error, and the square root function is monotonic, okay, meaning that for any two values, a and b, if a is greater than b, then the square root of a is also going to be greater than the square root of b. So basically, if there's a set of values that minimize the residual sum of squares, it will be the same set of values that minimize the mean squared error, and it will be the same set of values that minimize the root mean squared error. So that's fine, okay? And a lot of times we like root mean squared error because it uses the same units as the original values. So if you were measuring things in dollars, then root mean squared error is also measured in dollars. Whereas residual sum of squares, your RSS, would be measured in square dollars, and I don't know what a square dollar is, okay? It's dollars times dollars, right? Like $3 squared is 9 square dollars, but I have no concept of what that is. It makes, right? centimeters, sure, I can take a centimeter and I can square it, and that makes sense. But a dollar, how do you square money? I don't know. So root mean squared error is going to be back in the original units. Okay, so again, we're all familiar with linear regression. Linear regression, you have two parameters, the intercept W0, the slope W1. The value we're predicting is W0 plus W1 xn, and therefore the loss function, if I replace this function with this quantity, intercept plus W1 xn, this is what my loss function is. And now what do? We want to minimize this total, the mean squared error by finding the W0 and the W1 that minimize this function. So we say argmin, find the W0 and W1 that minimize this thing, and that's going to give us the set, our parameter values, W0 hat and W1 hat, okay? And I think you've done this in what, 100C or 100B or somewhere along the way you've done this, okay? And so, we can do this. We expand out this loss function, and you have all of these squared terms, and then you find the partial derivative with respect to W0. You find the partial derivative with respect to W1, right? So you do the partial derivative with respect to W1, the partial derivative with respect to W0, and you say, all right, we're going to find this location where the partial derivatives are equal to 0, and we have two equations, two unknowns, and we find the set of W0 and W1 that minimize these functions by setting the partial derivatives equal to 0. All right, so I skipped all of that because I imagine you've done that at some point. And so we skipped a bunch of these things. And if you want to see the actual work, you can look at section 114 in the textbook. Okay. We are going to kind of do the same thing in linear algebra, all right? And so we're dealing with a lot of kind of observations, and we have a summation term here for this loss function. It's the sum of all of these terms squared, right? These residuals squared. And having to deal with sums and stuff and derivatives can become annoying to work with. And if you work with matrices instead, when you do matrix multiplication, the summation is kind of implied inside that matrix operation. So for example, if you take a vector, W1, and you multiply it by a vector x1, or W and x, and you take those vectors, you're going to basically do, the cross product is, or the dot product is, you multiply each of these elements and then you sum them all together. Okay, and so it might have been a while since you took linear algebra, and if that's the case, you should spend some time reviewing it. And I highly recommend this playlist from one of my favorite YouTube channels, 3 Blue 1 Brown, and there is a set of videos. These are all excellent, and they really kind of visually capture a lot of core ideas from linear algebra that I think, it's easy to lose a lot of kind of the beauty of the math, and I think this channel really brings that back visually. So you should subscribe to that channel, like, comment, and subscribe, and watch these linear algebra things. Okay. All right, so we're going to do OLS with matrix notation. And again, if you've taken, say, 100C linear models or something, you've already seen this, but it's good to kind of go over it again. And we're going to be using a lot of kind of matrix stuff in this course, matrix computation things. Okay, so when we do OLS in matrix notation, we're going to say our parameters are in this vector W. So we have this vector W consisting of two terms, the intercept W0 and the slope W1. And we'll have a single observation, x sub n, and that's in this vector. and it's the first value is a 1, and the second value is the x value itself. And therefore, we can represent the predicted value, w0 plus w1xn, which is how we write our linear equation, as the product of w and xn. So w transpose xn is going to be w0 plus w1 times xn. So w transpose xn, this is our the result here, okay? And what we can then do is we can expand. We don't just have one observation, but we have a full matrix of observations. We have n observations. So I've got, if we have 100 observations, I've got 100 rows here in my X matrix. So I have a column of 1s and a column of X values. Okay, and then our target values will be, the actual values will be, the column of length n, this vector of values. And so the loss function is going to become t minus xw transpose times t minus xw. And so I will, so this is how we're going to show what the loss function is. And so, for example, so the predicted values, if I take my matrix of x and I multiply it by the vector w, the matrix of x values is this column of 1s and this column of x's, and I multiply by w0 and w1, I'm going to get one column of values. Okay, and these are all the predicted values. The intercept plus the slope times the x value, right? Now, one thing that as you're dealing with matrix notation is sometimes it can be confusing. Do I write xw or wx? All right, and so as you work with matrices, I strongly recommend, and actually in some of the homework problems I require, that you write the dimensions of the matrices underneath each of these things, okay? And that will help make sure that the order, right? Because you are used to, in just algebra, you can take, variables x and w and x, and those are the same. But that's not how it works with matrices, right? The order matters. And in fact, this is not even possible, okay? So in order to do matrix multiplication, the number of columns in this first element needs to match the number of rows in the multiplied element. And if they don't match, then you can't do this operation, okay? So x has n rows and 2 columns, w has 2 rows and 1 column, and so the result will have n rows and 1 column, okay? So the inner dimensions, that is the number of columns over here and the number of rows here, they must always match. And so, for example, here I'm going to take that column of years. So x is going to be a vector of length 28. So capital N is going to be 28. I'm going to create a vector of 1s, and I'm going to bind those two together. So now I have a column of 1s and a column of our x28x values. All right, so the dimensions of x, 28 rows, 2 columns. W is going to be just a column vector of 1s here, 1 and 1, 2 rows, 1 column. So W has 2 rows, 1 column. So I can do x times W. X times W multiplies out, and it becomes 28 rows, 1 column. N by 1 here, right? 28 by 2 times 2 by 1 becomes 28 by 1. That's right. But if I try to do the other thing, W times X, so this is W matrix multiply X, I get an error. It says error in WX, non-conformable arguments. So I'm trying to multiply a 2 by 1 by a 28 by 2. Okay, WX is not going to multiply, right? And so anytime you see this error, right? A lot of times students, when they encounter an error message in R, they just kind of throw up their hands and they go, oh, what's going on? But there's actually, the error messages actually contain a lot of helpful information. And in this case, if you ever see this error message, non-conformable arguments, it means the dimensions don't line up here. So you say, what are the dimensions of W? Dimensions of W are 2 by 1. What are the dimensions of X? 28 by 2. And you go, oh yeah, I can't multiply a 2 by 1 by 28 by 2. I have to multiply X times W for those dimensions to line up, okay? And so you can often kind of figure out these problems by writing the dimensions underneath each thing to make sure they align. All right, so anyway, I have xw, which is this n by 1 column of values. And I have the actual values t, and so t minus xw, is going to become the column of residuals, right? So this is also just one column of values. N rows, one column of values, all right? So a lot of times, we see something like this, t minus xw, and it feels like this is like the operations that we have to do. But you can also just look at this and say, oh, this is just the column of residuals. It's just the column of residuals. Okay, and so if I do the residuals, what are the residuals squared? The residual squared would be kind of this. I can get this by taking t minus xw transpose, which is going to be a row vector of length n multiplied by the column vector of length n, right? And so if I do t minus xw transpose times t minus xw, that's going to result in the same thing that we have here, which is just going to be all of my residuals squared. All the residual values squared. And if I want to take the mean squared error, I'm going to just take that value and do 1 over n, right? So if I do t minus xw, which is 1 by n, multiplied by t minus xw, n by 1, right? This is going to result in a single scalar value, 1 by n times n by 1. I multiply the elements, add them up. That's a single scalar value, and I can multiply by 1 by 1, right? So now I don't have to have this summation term. No need for a summation term. I can just do t minus xw transpose t minus xw, and that will represent my loss function. So far, so good? Okay. And so what I can do is I can do t minus xw transpose times t minus xw, and I can expand this out, right? So I don't know if you remember your transpose rules, but transpose of a sum or difference is just the sum or difference of the elements transposed. So it's going to be t transpose minus xw transpose, okay? And then the transpose of a matrix product is going to be the inverse order of the transposed objects, right? So you do xw transpose is going to be w transpose x transpose. Okay. So anyway, I have this t transpose minus w transpose x transpose t minus x times t minus xw. And then now I have this thing, and I would just kind of do first, outer, inner, last when multiplying these things. So I have t transpose t. And again, we want to kind of check the dimensions. T transpose is 1 by n, t is n by 1. Now I have t transpose xw, okay, and that multiplies out 1 by n by 2 by 2 by 1. And then I have w transpose x transpose t, and then I have w transpose x transpose xw, okay? And all of these, when you check the dimensions, they all become 1 by 1s, all right? They all become 1 by 1 scalars. And I can combine them all into a single thing, okay? And so our loss function is t transpose t minus 2w transpose x transpose t plus w transpose x transpose xw. And I can combine these two elements, t transpose xw and w transpose x transpose t, into just this one thing. And the reason why I can combine it is because both of these are scalar values, and they are transposes of each other. Okay, so the transpose of a scalar value is itself, the value itself, so I can combine those elements together. So yeah, t transpose xw and w transpose x transpose t are transposes of each other, and they're scalars, so we can just add them together. All right, is this okay, arriving at this thing here? Okay, so now that we have this loss function, let's try to use vector calculus to minimize it. Okay, so what we're going to do is we are going to take the quote derivative or the gradient with respect to the vector w. We're going to set that derivative or gradient equal to 0, and then we're going to solve for w. All right, so we're going to find where this this function has a gradient of 0. Okay, so if you think about how do we do this, all right? So with a derivative, you have a function that takes one real value and it outputs one real value, okay? And the derivative, the definition of the derivative is, you add a little value of h to x, and you say, well, how much did f of x change? F of x is here, and then when I add a tiny h to it, the function goes up by this much, right? So you take the difference between f of x 8 plus h and f of x. How much did these things change, right? And then you divide by the width of h there, okay? And you take this limit as h goes to 0, okay? We can rearrange these terms, and we say this is going to be equal. The derivative is if we kind of multiply, if I bring this over here, it's the derivative is going to be the f prime such that this satisfies this thing where it's equal to 0, okay? With a gradient, we now have a function that takes values from a higher dimensional space, so n-dimensional real vector. So in our case, we have a vector of two values, w0 and w1, and we want to find the gradient here, okay? The inputs are different values of the intercept and slope. We're putting in two values, we're getting one value, which is the residual sum of squares, or your mean squared error, okay? So we're taking two values in, intercept and slope, and we're saying what is the loss function, the total loss value. So we're going from higher dimensional space down to one value, and the gradient, this upside down triangle, we read as nabla, okay? So it's not triangle up, right side up is delta, triangle upside down is nabla, okay? And we're going to find the gradient, nabla f. And basically, we're taking this thing and we're just taking everything and turning them into kind of their vector forms of this. And we're going to find this where this thing is equal to 0. All right. Another way to think of this is if you have a function that outputs a scalar value, and you have the input is some vector w, the gradient with respect to w is basically going to be the vector of partial derivatives. So if w is w1, w2, all the way through wn, the gradient of f with respect to w is going to be the vector of the partial with respect to w1, the partial with respect to w2, so on and so forth. Okay. The gradient represents the slope of the tangent line, okay, or tangent vector of the function, and it points into the direction of the greatest rate of increase. And we'll take a look at this when we cover the gradient descent algorithm. But here are some useful gradient relations, okay? So let's say you have a function w, which outputs a scalar value, and that function is w transpose x. The gradient of w transpose x with respect to w is just x. Okay, what is the gradient? If the function is x transpose w, the gradient of x transpose w with respect to w is just x. If you have w transpose w, the gradient with respect to w is 2w. And then if you have w transpose matrix C times w, the gradient with respect to w is 2cw, okay? I have this derived, so you say, well, how do we know w transpose x with respect to w is x? Okay, so if w is w1, w2, and x is x1 and x2, w transpose x is w1, x1, and w2, x2. And if we say, okay, the gradient is the partial derivatives, so we're going to take this thing, what's the partial with respect to w1, and what's the partial of this thing with respect to w2? Okay, the partial derivative of this with respect to w1 is going to be just x1, right? And then this thing zeroes out because there's no w1 term. What's the partial derivative of this thing with respect to w2? Well, this part's 0 and this part's just x2. So the partial derivative of this with respect to w1 and w2 is going to be x1 and x2, and that's just your vector x. Okay? So, and then you can kind of go through all of these things. Same thing with w's, w transpose w will be w1 squared and w2 squared. And and the partial with respect to that is going to be 2W1 and 2W2, and that's going to just be 2W. All right, so anyway, we apply this to OLS regression. We say this is our loss function. So we derived this earlier on one of these slides. The loss function is here, okay? And now we have this loss function. And we're going to take the gradient of this with respect to W. We're going to set it equal to W and solve for 0, okay? So we're going to say, okay, what is the loss function with gradient of the loss function with respect to W, okay? So this zeroes out. The next term is going to be X transpose T. And this one, being W transpose XW, becomes 2 X transpose XW. And so this is my gradient. It's a 2 by 1 function. All right. And we set that equal to 0, and we're going to solve for W. So I have this. I set it equal to 0. If I set this equal to 0, I can multiply both sides by n over 2 to eliminate these constants. And then this one is negative, so I'm going to add that. And I'm going to get X transpose T is equal to X transpose XW. Now, in matrices, there's no division. You can't divide a matrix. But you can multiply by the inverse, right? And so when you multiply a matrix by its inverse, you get the identity matrix. So we're going to multiply both the left and right-hand side by the inverse of X transpose X. So I multiply X transpose X inverse here. This will become the identity. I'm going to just get W over here. Multiply this side by X transpose X inverse. So X transpose X inverse is going to be a square matrix, 2 by 2 square matrix. X transpose is 2 by n, and T is n by 1. And so when I multiply all of this out, I get a 2 by 1 matrix, which matches the dimensions of W. And so I get X transpose X inverse X transpose T. And that might be familiar to you already if you've taken 100C, and maybe not. This could be your first time seeing it, but this is your OLS solution. So the values of W, the estimate of values of W that minimize the loss function is going to be X transpose X inverse X transpose T. All right, oh, before I forget, last view quiz answer for today is the letter C. C as in cat. C as in cat is your final view quiz answer. C. Okay, and is that it? Huh, I wonder why this says 75 out of 77. Okay, well that is our final answer, our final slide. That is it for today's lecture, and so we'll wrap up there. Okay, I have posted kind of your first homework assignment, and the homework assignments are kind of long and challenging. We'll get to more stuff on Thursday, but you should be able to at least get started on some of this stuff here, okay? I'm looking forward to a great summer session with you guys, and we will see you guys on Thursday.